everybody. How's everybody doing this Friday? You guys ready to get started in a little bit here? Maybe we'll wait like another 1 or 2 minutes. See if anybody trickles in. Okay. We're going to get started, everyone. Get ready. If you're following along, get that handout ready to go. Today we're talking about state space representation of dynamic systems. This is probably the most popular way of mathematically representing a dynamic system. I'm going to write that at the top. I'm going to make a bold statement. The most popular mathematical representation of a dynamic system. So if you get a job in dynamics, out in industry, you're going to be working with this. The most popular mathematical representation of a dynamic system. So you might be saying, well, why is that? Well, let's talk about what it does a little bit. State space takes an nth order differential equation, and I'll abbreviate that. I'll just call it like a diff-EQ, and turns it into a series of first order equations, and turns it into a series of first order equations. And first order equations are easier to deal with than an nth order equation. And I'll list one other property for what makes state space so popular. And we'll get to this at the very end of our lecture today, but state space is useful for numerical simulation. In other words, if you want to know how a dynamic system is going to behave, usually we simulate it on the computer. That's already what we're doing in this class. We go into MATLAB, we make some graphs as a function of time, and we see what the system does. State space makes that easier to do on a computer. All right, so it's called state space, but what is the state of a dynamic system? What I'm going to do is I'm going to give you a definition from our system dynamics textbook. And they say the state of a dynamic system is the smallest. The state is constantly changing. Well, you're correct. The state is the smallest set of variables such that the knowledge of these variables, so the state is the smallest set of variables such that the knowledge of these variables at some point in time um, along with knowledge of the input function, whatever that is, like a force or something. So if I know these variables, and I also know, along with knowledge of the forcing function, the smallest set of variables, such that if I know these variables at some point in time and I know what the forcing function is going to be at some time, this determines the behavior of the system. I know this definition is a little wordy, so I want to give you an example. Okay. Throwing a ball. So let's say I'm standing out in a field and I'm throwing a ball. Let's talk about the state of this ball. The state could be the position of the ball, velocity of ball. So maybe we have two states. And so that's one of the things we need to know. And maybe we'll say the forcing function is the force from my arm when I throw the ball. So if I know what the force from my arm is going to be, and if I know, let's say, the position of the ball and the velocity of the ball when it leaves my hand, if this is the state of the system and I know this forcing function, then this knowledge determines the behavior of the system from that point forward. So I would be able to mathematically predict this is how the ball is going to fly through the air. And I know you guys have solved problems like this in like a physics class or something. You have a ball getting, I don't know, shot out of a cannon, and they tell you this is how fast it starts, and so you solve for the trajectory of the ball or something. We'll get to an example in a second, another example, to help clear this up. So the state variables, those are just the variables that make up the state of the system. So from this throwing a ball example, that would be the position of the ball and the velocity of the ball. Let's see. Oh, here, yeah, this is an important point I wanted to make. The number of state variables is equal to the order of the system. So when I say, okay, I'm going to throw a ball and there's two states, the position and the velocity, I'm assuming that that's going to behave as a second order system. So just like the number of initial conditions must be equal to the order of a system. So just keep that in mind. If it's like I'm making a state space model for a fourth order system, I'm going to have to define 4 states. Just like I would need 4 initial conditions. Okay, we're going to get right into an example to help show what state space form looks like. All right. So let's say we have here a second order differential equation, and you can tell because the highest derivative in there is 2. And like I just said, the number of initial conditions has to be equal to the order of the system. So I have 2 initial conditions. And the input to this system is u of t. That's like our forcing function. So let's define some state variables. And throughout today, I'm going to tell you some common ways of defining the states. You can be creative with state definitions, but I would wait until you get a little more familiar with state space. So for now, I'm going to show you some kind of standard ways of defining the states, and I would just go with those for now. All right, we're going to define 2 states, my friends, because this is a second order system. What I like to do use initial condition variables. Or that's not the way I want to say it. Use the same variables that are used for the initial conditions. So I'll have x of t and x dot of t. Those are the variables we use for our initial conditions. I'm going to use those for my states. So state 1, I have to use a different variable for this. So I'll call it z1 of t. And it's x of t. State 2, z2 of t, x dot of t. So just to be clear, z1 and z2 are my state variables. And I just set them equal to the same variables that I saw for the initial conditions. So this is the first step you do when you make a state space model, you define your state variables. Next, you take the derivative of these state variables, the first derivative. So if I take the first derivative of my first state, z1, well, that would be equal to x dot, right? And if I take the first derivative of z2, that would be equal to x double dot. Straightforward enough, right? But notice this. From our differential equation up here, I know that x double dot of t is equal to u of t, and then if I move that other stuff to the right hand side, minus 2x dot minus 2x of t, right? The reason I'm solving for x double dot by itself is because I want to plug it in here. So x double dot of t is u of t minus 2x dot of t minus 2x of t. So these are the first derivatives of my states. Okay, we're getting there. Next, we take these two equations above, but we write everything in terms of the state variables, which are z1 and z2, and the input variables. So you'll see what I do here. So z1 dot of t, instead of having it equal to x dot, I defined z2 up above to be x dot. So instead of writing x dot, I'm going to say z1 of dot is actually equal to z2. So now that first equation, it's in terms of purely state variables, z1 and z2. So now I'm going to do the same thing with z2 dot. So it's equal to u of t, which is an input variable. So that's okay if I leave that as it is. Now I have minus 2x dot, but x dot is, in terms of a state, it's z2. And then I'll have minus 2x of t, but x is our first state, z1 of t. Do you follow what I'm doing? So this, meh. Don't worry, we'll do more examples. A lot of examples today. So this already is what we call state space form. We started with a second order equation in terms of the variable x. Now we have two first order equations that are in terms of different variables, our two states. So it's two first order equations, but I guess the catch is we introduced like an extra variable. Instead of just having x, now I have z1 and z2. All right. Because we deal with linear equations in this class, one of the benefits of linear equations is you can write them in a matrix form. And this is what we're going to do next. So I have these two equations. but I'm going to stack them up so I have a vector of states. Z1 on top of Z2. So this is a 2 by 1 vector. 2 rows, 1 column. And we're going to say this is equal to a matrix times my state vector. So when we have a vector that's just our states on top of each other, Z1 on top of Z2, that's called your state vector, because it's just a vector full of your state definitions. All right. And then we're going to need another matrix, and that's going to be multiplied with our forcing function. And this can have a couple different names. Forcing function, input, sometimes it's called a control input, but it's just the external thing being applied to your system. So it could be a force, sometimes it'll be a source voltage, but in the problem it'll be clear what the external function is. Okay, let's put some little... Have you guys done stuff like this before? Sometimes in a differential equations course, they might teach you state space. Okay, so when you're putting this in matrix form, you want, let's call this first state equation 1 and this second state equation 2. You want this matrix equation to give back those same original equations. So like the top row should give back equation 1 and the bottom row should give back equation 2. So let's fill in this matrix together. From equation 1, I know Z1 dot is equal to Z2. So here in the matrix, I'm going to have Z1 dot is 0 times Z1 plus 1 times Z2. And Z1 dot doesn't depend on U. It just depends on Z2, so I put a 0 there. Z2 dot, if I'm looking at this equation, it's, well, let's start from left to right. It's minus 2 times Z1 minus 2 times Z2 plus 1 times U of T. And to test if your matrix equation is correct, you could just go through the exercise of multiplying this out. You guys have all done matrix like algebra before, right? Like this matrix right here, it'll give me 0 times Z1 of T plus 1 times Z2 of T. This one's going to give me minus 2 times Z1 of T minus 2 times Z2 of T. And then I'm going to have plus 0 times U of T plus 1, or rather, just 1 times U of T. And then if I add these two together, I'm going to get Z2 of T, and I'm going to get minus 2 Z1 of T minus 2 Z2 of T plus u of t. I'm sure you guys have done matrix multiplication before, but I just wanted to go through it if you hadn't done that in a while. But notice when I multiply out these matrices, I get these two equations, and these equations match the original equations. So it's writing the equations in this matrix form is equivalent. It's just a different way of organizing the results. Any questions about that? Okay. We're going to do more examples, so let's introduce some terminology first, though. So I showed the state vector, this matrix. Then what do we do with those matrices? Ooh, that I will show you towards the end. Actually, on the next page, I'll show you a usefulness of this matrix right here. This matrix we call the A matrix. It's the matrix that multiplies with the state vector. Another name for it is the system matrix. It's the most important of these matrices. And this one that multiplies with the forcing function, we call it the B matrix. Okay. Let me... So this equation that we wrote, it's called the state equation. So let's write it out like this. Z1 dot Z2 dot is equal to A. Maybe I'll put like a box around it so you see it's a matrix. Times Z1 Z2 plus B times U. And we can write this in an even more condensed way as this vector notation. So there's different ways to denote vectors, but this is a popular way. I think it's an easy way. Underlined means vector. Sometimes people write an arrow on the top, but I think that arrow can get in the way of the dot on the top. And plus it takes longer to write. You have to like draw that squiggly thing. I think just doing a line underneath is faster. It's one of the popular ways. And I'm going to put a line here underneath the input as well. Like in our example, there was just one input to the system that was U. And so it's not really a vector, but sometimes you can have multiple inputs to your system. Like if you think about an airplane, if you ever look at the wings, there's multiple surfaces on the wing that change to affect the motion of the airplane. You could think, so they call those the flaps. They lift up and down, and there's more than one on each wing. So those could be considered like different control inputs. And then you have the rudder at the back of the plane. And that's another input to the system. And then even another input is the thrust coming out of the engines. So for an airplane, you might have, at least a dozen control inputs affecting the system. And you could define close to as many states for an airplane, if not more. I think we'll do an example of putting some equations for an airplane in state space form once we get a little more adjusted. Okay. So I've been writing the state vector as a z, and now I'm just realizing in my notes for the type set I put an x. Let's just make it a z. Oops. Go away. And I'll underline it, z. And I'll do the same thing here. Z. Ailerons. Yeah, exactly. Yet another control surface on an airplane. So you have many, many, many control inputs. So this will definitely be a vector for many applications. Okay. So let's go through this table. So Z, this is our state vector. U, we'll call this our control input vector. A is our system matrix. It actually has another funny name. I don't know really where this came from, but you can also call it the plant. Just call it the plant. Maybe from like a chemical plant or something. Chemical engineers use this state space representation as well to model different processes. Okay, the B is called the control influence matrix. Because this matrix describes how the different control inputs interact with the states. How they influence the states. So you may find from the B matrix that the control input doesn't affect certain states directly. Actually, we see that in the very first example I did. Because here's our B matrix. It has a 0 entry for the Z1 dot state. So the control input doesn't directly affect Z1. It affects Z2, and then Z2 affects Z1. Okay. We have to talk about the dimension of these matrices a little bit. This will get easier the more we practice, but okay, the state vector. The number of states is equal to the order of the system. I said that at the beginning of the lecture. So the order of a system, we usually say it's n. So the state vector is going to be n states stacked on top of each other. So it's going to be an n by 1 matrix. N rows, 1 column. So if you look like up here, that was a second order system. Our state vector was 2 states stacked on top of each other. So it's 2 by 1, where n is equal to 2, the 2 states. Okay, the control input vector. So the number of inputs to a system, we usually call that R. So for an aircraft, they might be like, okay, R is equal to like 8 inputs or something. Often in this class, we'll just deal with 1 input. Okay, this is a question for the audience. What dimension do these A and B matrices, the system matrix and the control influence matrix, need to be in terms of N and R, those variables I defined up above? A little test of your matrix algebra. What dimension do they need to be? Okay, Aaron says R by N. For which one? A or B? For A. Okay, Aaron says R by N for A. You're close. You're half right. So let's look at this right here. So I know that this vector is 2 by 1. And I know that my state vector is 2 by 1. And let's limit ourselves. Let's forget about the B times U for now. But I know the left-hand side has to be equal to the right-hand side. So a 2 by 1 has to be the result of multiplying the A matrix with another 2 by 1 matrix. So what size matrix has to multiply with a 2 by 1 so that we get a 2 by 1 back? Two by 1. Thank you. That is correct. This would have to be 2 by 2 if I want to get back a 2 by 1. There's a little trick you can do. I use this all the time. So, okay, I got a 2 by 2 times a 2 by 1. You can only multiply a matrix together. You can only multiply 2 matrices together if these dimensions match. So because this number's a 2 and because this number's a 2, I'll be able to do matrix multiplication. If those numbers didn't match, it'll throw you an error. The dimension of the resulting matrix is these two numbers. So if I take a 2 by 2 and multiply with a 2 by 1, I get a 2 by 1 back. So in general, I'm going to have an n by 1 on my left-hand side, and it's going to be my A matrix times another n by 1. So if I want to be able to multiply these two matrices together, well, if I want to be able to multiply them, first, this dimension has to be consistent in. Because if these numbers don't match, then you can't multiply them at all. So I know this has to be by n. And I know the resulting dimension should match this one. Overall, it should be an n by 1. So that means this dimension has to be n, so that I get an n by 1. So all that to say, our A matrix, if we have n states, the A matrix has to be n by n. Meaning it'll always be a square matrix with the same number of rows as columns. Okay, now I'm going to test you again. Because what size does the B matrix have to be? We know that it's going to have to give back an n by 1 and B is multiplying with an r by 1, which is, our u vector. So what size does B have to be? There it is. Aaron's got it. If I take an n by r multiplied by an r by 1, well, first, these r's had to match to make these matrices compatible for multiplication, and the result of that will be n by 1. Boom. Well done. Okay. So that's some terminology, some matrix size stuff. Phil asked earlier, what do we use these matrices for? Well, I want to show you the first special property. The eigenvalues of the A matrix are the roots of the characteristic equation. Let's talk about what that means. So this was our second order system. Let's forget about state space for a second. If we wanted to solve this like we've been doing so far in the class, we'd get the characteristic equation, which would be lambda squared plus 2 lambda plus 2 equals 0. And then we'd go over to MATLAB and we'd say, okay, what are the roots of 1, 2, 2? So it's minus 1 plus or minus I. Okay. Well, what was our A matrix again? Let's go back up. It was 0, 1, minus 2, 2. Oh, minus 2, my bad. Well, let's calculate the eigenvalues of the A matrix. We're not going to do that by hand in this class, so you can just breathe a nice sigh of relief. We're going to use MATLAB. And the command in MATLAB is eig of A. So let's go do that. A equals 0, 1, minus 2, minus 2. So that's how you make the matrix. And then I want to get the eigenvalues, so I do eig of A. And voila! Look familiar? The eigenvalues of A are the roots of the characteristic equation. In fact, what I think is that when you use the roots command in MATLAB, they build a matrix like this and they calculate the eigenvalues. And that's how they calculate the roots of your system. Because it's there's very efficient algorithms for getting eigenvalues of matrices. So that's like the easiest way for a computer to calculate the roots. So just roots of characteristic equation are the same as eigenvalues of A. Where A is our system matrix. A very important property. Are you guys ready for another example? We're going to do fourth order. Holy smokes. All right. So we have a fourth order differential equation. We have I'll call it a control input acting on the system. You could make it a sinusoid. You could make it a step input. This is just like a placeholder for any function that might be applied to the system. And because it's fourth order, we have 1, 2, 3, 4 initial conditions. Let's put this in state space form. So a popular way to define the states, let's call them Z1, Z2, Z3, Z4. We know there's going to be 4 of them. Is to have the first state just equal to the dependent variable, x. And then you make the subsequent states equal to the derivatives. And you only have to keep going until your number of states is equal to the order of the system. So I didn't have to go all the way up to the 4th derivative of x. So you start with x, like the 0th order derivative, and then you just keep going until you reach n. So n equals 4 state variables. All right. So we're taking the same process as we did for that second order system. So the next step, we're going to take the derivative of each of our state variables. So the derivative of our first state is the derivative of x, which is x dot. The derivative of our second state was x dot, so if I take the derivative of that, it's x double dot. And you see how this is going. The derivative of my fourth state is now x quadruple dot. This dot notation only goes so far. I think 4 is the highest I would go, and then I'd probably use that d dt instead. It can get out of hand. All right. So we took the first derivative. Here, let's write out what x quadruple dot is using this up here. So x quadruple dot is minus 3 x triple dot minus 33 over 4 x double dot minus 21 over 2 x dot plus 17 over 2 x. Oh, I put a plus, that should be minus. Plus u. So I'm just using the original differential equation to write out what x quadruple dot is. Okay, now just like before, we're gonna take these 4 equations, but just rewrite them so that they're purely in terms of our states. And you can also use your inputs, which is just u. So z1 dot is x dot, but that's the same as z2 if you look up at our state definitions above. And z2 dot is x double dot, but that's what we called z3. Z3 dot is what we called z4. And then z4 dot, this one's going to take a little bit more work because it's minus 3 times x triple dot. X triple dot was z4. 33 over 4 x double dot was z3. X dot was z2. X was just z1. And then u, we don't have to do anything with it. Not too bad. Okay, I'm going to set this up for you. But I want you to fill in what these matrices are, just so you practice building it. Think about what size this matrix has to be. The shapes that I'm drawing for each of these is kind of a hint to their size. All right, so on your own, take like a minute or two and try to fill in the A matrix, the system matrix, as well as the B matrix, the control influence matrix. And then we'll double check with what I do. We'll turn up the music a little. Thinking music. This artist is Elijah Nong, or Elijah Nang. It's gotta be Nong. I discovered his stuff yesterday, and it's such a cool, smooth groove with a Japanese influence. I love it. And he has really great animations for these videos as well. This is the background for this YouTube video. Beautiful. All right, did you fill it in? Do you feel confident? So this matrix, what size is it? It's going to be 4x4. 4 states. A has to be 4x4. Very good. All right. 0, 1, 0, 0, 0. So what I just filled in is our Z1 dot equation. So up here, Z1 dot is just equal to 1 times Z2. So it's 0 times Z1 plus 1 times Z2, blah, 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 blah. Z2 is equal to Z3. Z3 dot is equal to Z4. So 0 times everything except for Z4. And this one always takes a little more work. -3. Oh wait, I did this wrong. -17 over 2 times Z1, -21 over 2 times Z2, -33 over 4 times Z3, -3 times Z4, plus, oh wait, I should have put a 0 over here, plus 1 times U. Do you guys get the same thing? I'm sure you did. It was too easy for you. It was just too... It was too simple. I'll point this out, maybe not today, but later on. But there's... for different types of systems... Oh, thank you, Phil. You're too kind. Like for mechanical systems, there's kind of standard ways that this A matrix will look. Like you see this diagonal of ones going across. You'll notice for different systems, there's like certain standard patterns that come out. And people have found efficient ways to build these A matrices. I actually have an example. I did a little, you know how we did an example of a skyscraper as a potential higher order system? So I made a code in MATLAB that builds a skyscraper and then exposes it to an earthquake. So we might get to that later on. but it builds a very big A matrix. So maybe we'll point that out later on. Okay. So let's go to a physical system. We're going to go to this RLC circuit. And we've modeled this before, but now I want to go back and do it in state space. Let me pull up a cheat sheet on the side. Alright. So to remind you of what the RLC circuit looks like, well, there's different configurations, but I'm going to show you the series configuration where it's the resistor, the inductor, and the capacitor just all linked together like that. And I'll just define current going this way. It doesn't really matter what you choose. Alright, and then we'll put some like reference points on here. This is useful when you do your loop rule. Okay. We'll just quickly blast through this. I'm gonna go this, well, actually we could go the opposite way. Why not? That'll be good practice. I'm gonna go from D to C to B to A, back to D. The last time we did this, I did a loop the other way. Okay, so the loop rule says this. Okay, D to C plus V, C to B plus V. I'm gonna turn on this music a little bit, that's a little loud. V, B to A plus V, A to D. All of those voltage rises and drops have to add up to 0. That's the loop rule. Okay. So if I go from D to C in the opposite direction of the current, so my loop is going this way. I'm going to cross the capacitor in the opposite direction of the current, so I'm going to call this positive VC plus VL. If I was going the other way, it'd be minus. When I go across the resistor, I'm just going to use Ohm's law in there. It's going to be plus RI. And then when I go from A to D, I cross the voltage source, but I go from the plus to the minus, which means I subtract the source voltage. So that's our loop rule. It's going to be 0. VC plus VL plus RI minus VS equals 0. Oh, and by the way, you're going to notice modeling this circuit, when it gets to the actual equation, it's easier this way, I think, doing it in state space than what we had to do before. So, okay, the capacitor element equation. So this is just saying VC dot is 1 over C times the current. That's what we call our capacitor element equation. It never changes. Same thing with this inductor element equation. It's the, I dot is 1 over L VL. Okay. We're going to define our state variables here. Actually, I think I have a box at the bottom of this page. Aha! Why don't we do this first? I'm realizing I want to give you some of these general rules. When you're doing state space for electrical dynamic systems, so you're looking at a circuit, there are standard ways to define the states. This is like the easiest way to do this. I learned this from Dr. Mook, if you guys know him. Define states as the voltage drop across each capacitor, so in other words, VC, and there might be more than one capacitor in the circuit. So if you have two capacitors, you would have two states, the voltage drop across each. And you also define a state for the current through each inductor. Maybe I'll call it I sub L just to be clear. It's the current going through an inductor. So this is kind of cool. You can determine the order of an electrical system just by counting the number of capacitors and inductors. Because, so remember, the number of states has to be the same as the order of a system. Well, it turns out the order of an electrical system is the number of capacitors plus the number of inductors in the circuit. So order of electrical system equals number of capacitors plus the number of inductors. So you can use this trick to impress some of your friends if you have very nerdy friends, maybe. For example, what if I make this crazy looking circuit? It's got an inductor there, it's got a capacitor over here, it's got another inductor, another capacitor, an inductor, a resistor, and then another capacitor in over here. And it's like you have R1, L1, L2, L3, C1, C2, C3, source voltage. And I ask you, okay, look at this crazy circuit. What order system is this? And you say, what do you say? Yeah. Yes. Sixth order differential equation. Yes. It's a little trick. I guess you can do the same thing with mechanical systems. I think I told you earlier, just as an aside, I mean, if you have spring mass systems, and you might have a couple connected together, we use this for all sorts of different modeling. Each mass that you see in there contributes 2 orders or 2 states, because a typical state is like position and velocity, and each mass is described by those 2 states. So like this is a 6 order system. Okay. So whenever we go into a circuits problem, it'll be a little less intimidating because you'll know in advance what order it is, and you'll also know how to define your states, because you define your states, the voltage drop across each capacitor, so that's VC, and the current through each inductor. So let's go back to this problem. And now you know this series RLC circuit is just second order, because there's one inductor, one capacitor, you add that up. And we define our state variables. Sure, let's call it Z1 as the voltage across each capacitor, so there's just one state for that. And then the other state is going to be the current through the inductor. Well, the same current, because there's just one loop, the same current's going through everything. So we'll just call it I. So 2 states, second order system. Okay, now just like we did with the previous 2 examples, we have to take the derivative of these state variables. So Z1 dot is VC dot. And this is where our element equations come in, because I know that VC dot is 1 over C times I. All right, let's do our other state. Z2 dot is I dot. Our other element equation comes in handy. 1 over L VL. Okay. So easy enough so far, right? Next, to get our standard matrix form, all of these variables have to be in terms of state variables or input variables. So if it's not clear, the input variable for this problem is the source voltage, Vs. So that'll be defined in advance for you. And then our state variables, well, we just did those up above. So, for example, well, let's do this one first. Z1 dot is 1 over C I, and I is Z2. So, very nice. We're done with that equation. It's in terms of our state. Then Z2 dot is 1 over L VL. But here's the problem. VL is not a state. So what the heck are we going to do? Look up here. We're going to go back to our loop equation. Boom. VL is minus VC. VC is a state. Minus R times I. I is a state. And plus VS, where VS is an input. So, if we take that, take it down here. So this is equal to 1 over L times minus VC minus RI plus VS. Then I can say that this is, so VC was Z1 minus Z1. I was Z2. Cool. Minus R Z2. And then VS is our input. So I can just leave that as well. Ooh, I didn't really leave room for us to put this in matrix form, though. We can squeeze it in somewhere. Whatever, why don't we put it... I'm gonna scoot some of this info over. Get over here. And then we'll take this and put it in matrix form here. Okay. Z1 dot Z2 dot equals, we know this will be a 2 by 2 matrix. Z1, Z2 plus, and then I'll put this VS. All right, so Z1 dot is equal to 1 over C times Z2. So 0 times Z1 plus 1 over C times Z2. And it doesn't depend on the source voltage. So I put a 0 there. All right, Z2 dot is minus 1 over L times Z1 minus R over L times Z2 plus 1 over L times VS. Whew! So at the top of this example, I said this is the easiest way to model an electrical system. And maybe it doesn't seem as easy right now, but once you get to a bigger circuit, this is going to make your life so much easier than doing this any other way. Now, if you don't like replacing physical variables with these Z1, Z2, because it's like, what is Z1? You can also just write this as, so in terms of the physical variables. So like VC dot I dot 0, 1 over C, minus 1 over L, minus R over L. VC I. And this is actually how I usually do it, just so I can keep track of what everything is. Just seeing everything in terms of the physical variables themselves. Pretty cool, right? So if you want to see, is my system underdamped? Is it overdamped? Is it critically damped? What you can do, you say, okay, I know I have this capacitance, this resistance, this inductance. You build that matrix, throw it into MATLAB, get the eigenvalues of that matrix with one line of code, and then you'll know how your system's going to behave. You're going to know its settling time from the roots. You're going to know if it has oscillations in it. All of that good stuff. So you learn a lot from this A matrix. Whoa, we haven't taken a break at all. We've just blasted through content. I think I just have one more page after this, right? Let's take a 5-minute break, come back at 3:33 Eastern. No breaks? You don't want a break? Should we have a vote? You're crazy. You've lost your mind. We'll take a short little break because we only have a little bit more to go. This is going to show some of the numerical benefits of state space. We'll take a short little break. I'll be right back, my friends. Get a drink of water. Do some yoga. Grab a coffee. Go do a cartwheel. All right, are you guys prepared? We are going to talk about one of the most beautiful benefits of state space when it comes to computer simulation. All right, get back, get focused, get your hand out right in front of you, be ready to follow along. Okay, so why are we doing state space? One of the reasons is it's a convenient mathematical form for doing numerical simulations. So I'm going to show you the very most basic way of doing a numerical simulation with state space. Have you heard of the Euler forward method? You probably have at some point. And even if they didn't call it this method, I think you might be familiar with it. So I'm going to show you how you apply it to a first order system. So look at this. We have x dot plus 3x equals u of t. And u of t, once again, it's like a placeholder for any type of external forcing. It could be a step input, it could be a ramp input, it could be a sinusoid, it could be just like a random signal. And here's our initial condition. All right. Let us consider the forward difference scheme. All right, look at what this says. This says that the variable x at some time, like let's say that we are at a time t naught right now. Maybe it's like 5 seconds or whatever. This is saying if I go into the future and amount delta t, then where you're going to be delta t from now is where you are right now. So like, let's say x at t naught, that's x right now. This x t naught plus delta t is a little bit in the future. So just a little bit further away from right now. That's going to be where you are right now plus your current rate of change times the time until this is not the way to describe it. We'll just call this a small time duration. So you guys have seen something like this before. Like it'll come in an example like this. You're driving, or let's say I'm driving on a racetrack and I'm 200 meters down the stretch. So let's say I'm like 200 meters into the race and I'm traveling at 60 meters per second. You might say, okay, how far am I going to be a second from now? So you'll multiply this by like 1 second. So by this prediction, if I travel 60 meters per second, I'm at 200 meters right now. 1 second from now, if I maintain that speed, I'll be at 260 meters. So that's all this equation is saying. It's an approximation of, if you know your rate of change, where are you going to be in the future? So if we apply this to this differential equation right here, this is a little bit different. Okay, let's do this. Let's start at t naught equals 0. So I know that x at that time, it equals 0. Like, that's for my initial condition. x0 equals 0. So what is x at 0 plus delta t? So like a little step forward in the future. Well, I know that that should be x at 0 plus my rate of change at 0 times that little time difference. Well, okay, for this equation, I know that for my initial condition, x0 is 0. How do I get this, my rate of change at 0? Well, you could use our original differential equation. So if I take this, x dot of t is equal to minus 3 x of t plus u of t. So that would imply that my rate of change at time equals 0 is minus 3 times x at 0 plus whatever my input is at 0. Hello, Thor's lost kitten. Welcome to the chat. So here I would plug in minus 3 times x0, which I know is 0, plus u0, whatever my input to the system is at that initial time. All right, so maybe we'll gather these terms together. So it'll equal u at time 0 times delta t. And then, so this is what my prediction of x is at delta t. Then if I say, so you just continue with this recursively. So what is x at 0 plus 2 delta t? So like 2 time steps from now. Well, actually, I want to write it like this. So from the first step, I advanced forward delta t. And what if I advance forward again from that position? Well, I'll have x delta t plus x dot at delta t times delta t. So x at delta t, which we got from our previous time step, was u naught times delta t. And then if we do x dot at delta t, like if I go back up here, x dot at delta t would be minus 3x at delta t plus u at delta t. So I would take minus 3x at delta t plus u at delta t times delta t. Is this making sense? It's actually a beautiful thing. Because if you know your initial condition, and if you know like what your input to the system is at each time, you can make a code that does this in MATLAB. Yep, love the tablet usage for explanations, by the way. Oh, thank you very much. How about, before we show how you apply this to state space in general, how about we take this into MATLAB? We'll take the same equation and I'll show you how this works. Prepare yourself. Okay. So let's say x0 is our initial condition, and I'll say it's 0. And let's make a time vector over which we're gonna like simulate this system. So let's say we're gonna start at time 0. We're gonna go at intervals dt, and we're gonna go up to, I don't know, maybe 1 second. And let's define dt. Let's do this in increments of 0.01 seconds. So that's like 100 times per second. Or increments of 100th of a second. So this is our time increment. This would be the time vector over which we solve differential equation. This is our initial condition. Now the way we're gonna implement this, been ages since you've seen MATLAB. Welcome back. Welcome back. It misses you. Okay, I'm gonna define another variable. I'm gonna call this capital N the length of my time vector. So, number of elements in time vector. That's all the length does. And we already know this should give what, like 101? If I go from 0 to 1 in 0.01 second increments, I think that's 101. We could run it. N is 101. Okay. Have you guys used for loops before? Let's explain this. So this is how I'm going to do Euler forward for this equation. X, each time I go through the loop, been a little while. Is going to be, remember, or maybe I should do it this way. This is what Euler forward does. It says X, my variable, one time step in the future is equal to my variable right now plus my rate of change right now times the time interval. So, I mean, just conceptually, this is the Euler forward equation. X in the future is X now plus the rate of change times my time interval. And what the for loop does is it just says, okay, I'm gonna keep doing this operation over and over and over and over again until I've cycled through all of the times that I want to solve for. And it's kind of cool if you look at this. Each time you go into this for loop, this k parameter updates. So the first time in this loop, k is going to be equal to 1. So it's going to say like my second x value is going to be my first x value plus, you know, this stuff at the first. And then the next time through the loop, my third value is going to depend on my second, and so it just builds on each other. Okay, we're going to need this too. So from our differential equation, x dot at any time is minus 3 times x at that time plus u at that time. If we do a unit step input, then we could say that our control input at every time is just like u is equal to 1. If control is a unit step input. So every time we go into this loop, it's going to say, okay, my input, it's still 1. We're just holding it steady there. So my rate of change should be minus 3 times that plus 1. xk plus 1. All right, let's see if this works. So I'm going to do a plot afterwards, and I'm going to show my time vector and well, we're going to show x. The initial is wrong, isn't it? x0 initial condition. Oh, okay. I have to say x1 equals whatever I define that to be. u1 x dot 1. Thank you. Okay. Let's do a little fancy stuff. Let's beef up that line width. Let's turn on the grid. Let's label our axes. Y label. That's x of t. Let's even give it a title. Using Euler forward method to get step response. Let's go. MATLAB always gives you an error your first time, but oh, it worked. No worries, that's why I never get used to live coding lectures. So what x are you plotting? Let me tell you what I'm plotting. Actually, you know what we could do? So what I'm doing, x0, x1, x dot. Oh, okay. All of that in the code, I don't see just x. Oh, okay. So when you see these numbers following x, actually I'll show you over here. What I'm doing, I'll draw this off to the side. So when we solve this differential equation, we're looking for x of t. And in this simulation, I'm saying, like, let's just look at the solution over this range, like t goes from 0 up to 1 second. Well, in MATLAB, the way that I have to do this is I have to break x into a vector. And it's going to be x at time 0, and it's going to be x at delta t, x at 2 delta t, and it's going to go all the way up to x at 1 second. And this first element of this vector. In my code, I call it x1, just like for the first index. So if you see x1, it's the first index of x, and it means the initial x value at time is 0. And this one would be at index 2. And then we saw that the length of the whole thing was 101 elements. So this last one is x101. Does that help you? It's a little tricky. But can you go back to the code? Yeah. X at t equals 0. This way of solving an equation where you like do it iteratively, where each step builds on the previous step, that's what people mean when they say a numerical solution. This is how we solve a lot of equations in practice. Like, the way we've been solving equations like this so far in the class, and we'll continue to do it that way, is we analytically solve it, meaning you get the homogeneous solution, you get the particular solution, you add those together. I want to solve this equation the same way that we've been doing in the past, homogeneous particular, and compare it. All right, I'm going to leave the code. I'll post that code. We'll go back to it in a second too, but let's quickly solve this the way we're used to on the side. And so I said u of t was a unit step input, right? So if you could first do the particular solution. I know that x p of t, it's going to be a constant. So if I sub this in, I'm going to have 0 plus 3d equals 1, so d equals 1/3. So that's the particular solution. If you do the homogeneous, I'm going to have we'll first do the characteristic equation, and you find the root. And then that means the homogeneous solution. I'm out. Happy Friday. All right, see you, Phil. So x homogeneous of t is some coefficient a, e to the minus 3t. So the complete solution is x of t is the homogeneous plus the particular, which is a e to the minus 3t plus 1/3. And then if we want to get this coefficient, we use the initial condition, x of 0 equals 0, and that'll equal a plus 1/3. So a is equal to minus 1/3. So that means x of t is minus 1/3 e to the minus 3t plus 1/3. So I want to put this in my MATLAB code, and I want to see how it compares to this Euler forward approach that we did. Okay, so the way I do that, I don't need to use a for loop. I could just say x analytical is minus 1/3 times the exponential of minus 3 times our time vector plus 1/3. And let's go to our plot. Let's plot the analytical one first. X analytical. And I want to put that in black. And then I'm going to plot the other X we got in red. Actually, maybe we'll do red circles. So now I'm going to add a legend to distinguish between these two lines that I'm putting on there. So I'm going to put the analytical solution and then the other one that we got from Euler forward. Let's try it. Pretty close, right? They're right on top of each other. Well, not exactly if you zoom in. Because when you do these numerical methods, they're always going to be approximate. Are you guys keeping up with me? Or does it just seem like crazy talk to you? So I kind of went down a rabbit hole there, but I wanted to show you this is all supposed to come back to state space, but I wanted to show you how a numerical method works on a first order system because it's easier to explain it with that. But when we do state space is a first order system, but it's like a matrix first order system. Yep, sorry, working on a model while listening. That's okay. So state space has a first order matrix equation. But this forward difference scheme still works, even for a matrix. So I can say like this vector, and it could be filled with 100 different state variables. If I want to predict where it's going to be a little bit forward in the future, it's going to be whatever the vector values are right now, plus the derivative of those vector values right now times delta t. And this, so let's rewrite this, plus, so this is from this equation up above, it's our A matrix times our state vector at t naught plus B times our input vector at that time times delta t. So I could take a potentially big 100th order state space system. And when I write a code to predict the next step of those 100 whatever states, when I write that code in MATLAB, it's not going to be very much harder than the other code we just wrote for a first order system. And that's the beauty of state space. Let me show you. Okay, we're running out of time. I'm going to show you my little earthquake simulation. It's based on this very same principle. Are you ready? Prepare yourself. Let's start with 2 floors. I won't go too much into the code here. I'm just going to run this and show you what it does. But it builds a state space model for a building using a sequence of spring mass systems. It uses like an Euler forward method, and then it animates the result. So these are like the 2 floors shaking relative to each other, assuming that the earth is shaking underneath. And if I make it, let's make it 5 floors. I made it really wobbly. Okay, but we could make it 20 floors. Oh, now it's looking a little more like continuous, right? This is more a jellyfish of a building, but this is how we model buildings. We just make them probably a little more stiff. Do you guys want to see what the A matrix looks like for this? A. Well, what's the size of it? 40 by 40. What's the input there? Yeah, I'm just doing a sinusoidal input to the first floor. Now, look at this. If I get the eigenvalues of that, those are the roots of the characteristic equation. Oh wait, why don't we try... Okay, I'm gonna say lambda is eig of A. I wanna try something. Let's plot... I want to do a complex plane plot of the roots so you guys can see where all of the roots are for that building. So the horizontal axis will be the real part of the root. The vertical axis will be the imaginary part of the root. And let's put them with x's. Let's make the line width 2. I wish my research would wiggle buildings now. You can just change your research. Marker size 6 maybe or something. Ooh. These are the roots. All of them have negative real parts. So the system's stable. Which ones are the dominant roots? Well, the ones with the smallest real part. So they're going to be like over here. So these 2 would be the dominant roots. But you guys already have the capability. If I tell you what all of these roots are, you could write the homogeneous solution for this building. It looks like all of the roots are a complex conjugate. So it's a bunch of underdamped systems combined together. Oops, I went to the wrong thing. Let's make it 100 floors. Go, 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 go. Is it working? Oh. It's slowing down my computer a little bit. You see like those traveling waves coming up? Because it's like spring mass systems connected all together. And each one affects the next one. But it starts from the ground and works its way up. Okay, I better quit this before it explodes my computer. But I show that to you just as an example of that's the kind of numerical simulation you can put together pretty quick with state space. I'm not an earthquake specialist. But because I played around with this stuff quite a bit, I can put together something like that pretty quick. You guys can as well. I know some of you have made some sweet MATLAB programs already. It is not outside of your reach by any means. Thank you guys for your attention today. It's always a pleasure to hang out with you in this virtual domain. I'm going to hang out here until close to 5 p.m. Any questions you have, I'm happy to take those. You're welcome to just hang out as well. I hope you have a good rest of your Friday. Thanks. What course is this for? Math focused folks. It is called Dynamic Systems. And it's a mechanical engineering course. Or aerospace engineering. It's applicable to both. Actually, any kind of engineering, I think this stuff is useful. What are you working on, Thor's Lost Kitten? You mentioned that you're doing research. Are you doing mathy things? Statistical natural language processing? Wow. I don't know what that means. Statistics is math, though. Basically, question answering systems and similar machine learning models. Wow. Oh, nice. Are you familiar with that virtual assistant thing on Twitch? I thought that was a real person. It's some AI thing. It would come into this channel and like talk to me, and I would talk back and be like, "Oh, how are you doing?" Well, it fooled me. It was good enough to confuse me that I thought I was a real person for a while. Where's that thing? Yeah, the recent models can be pretty gnarly, especially for short text interactions without much need for reasoning. Yeah. Yeah, just like casual Twitch chat kind of stuff. Thanks for the link. What's your research focus when you're not teaching? I've done, like in my PhD, I did some work with control systems for flexible structures. So maybe like a satellite, maybe like a panel on a satellite, where they're trying to make those structures really light, but maybe very long as well. And so as the satellite moves, the panel tends to like vibrate. And so how can you program some actuators to minimize those vibrations? So that kind of stuff. But more recently, I'm interested in game-based learning. So how can you help people learn through video games? And it doesn't have to be a video game. Could be any kind of game. But video games are a very good medium. Like I teach a road vehicle dynamics class, so it's about cars. And we're very fortunate at UB. We have this driving simulator. It's on a motion platform. So we made a couple games that students in this class play on the driving simulator. And it's meant to teach them about how the car performs. So it's not just like a driving game. There's some learning element integrated with it, even though games just in themselves teach you a lot. So I've done some research on like how do students respond to that driving simulator, and how does the game design how can you change the game design to help students achieve the learning outcomes you're going for? I thought you meant game theory for a second there. Yeah, but the human interaction is pretty interesting. Yeah. There is a conference that I want to attend. It's online. But this academic community, I guess it's a professional community too, but they study how can we use games to train people. Even the military is interested in this. Like, the military has a huge presence at this conference. We had a postdoc in our group that worked in a similar space. I think he went there last time. Oh, nice. I went to this, I think it was 2 summers ago. I don't know why I didn't go last summer. He was focused on educational games for industrial instruction, employee onboarding, and VR. Yeah. Yeah. Yeah, like they have this whole track on the corporate, nonprofit. I'm also interested in assessment. So, like, I want to go to this session. Like, how do you actually measure how people respond to this stuff, and what should you be measuring? Oh, it's fun. Escape rooms. I've done an escape room before in the classroom. IIRC assessment was the hardest part to formalize and describe. Yeah. People, there seems to be a consensus that games are helpful for learning because it's like active learning. Active learning has all these benefits in the academic literature. But then there's all these papers about, well, there's no empirical data that's supporting exactly how this thing is working. And I don't know. Oh, see you. Thanks for stopping in.
杯を交わして互いの友好の証とする原告の同胞の儀式だ。酒は嫌いか？
大好きです。これで第7と第8は友となれたわけですね。
よろしくな。
All right, everybody. I think I'm gonna call that the stream. Thank you for hanging out. Thank you for your attention. Hope you learned something valuable today. Have a great weekend, everybody.